Welcome back to the video lecture series. This is Dr. P SREENIVASULU. In signal systems, we are going to discuss this video lecture series for signal systems. Now, already we discussed about what is the Laplace transform, the importance of Laplace transform, and properties of Laplace transform. Now, today we are going to see some problems on this Laplace transform. First, you see, find out Laplace transform of an exponential function. It is given f of t is equal to e power at u of t. Usually we need to write e power at u of t. Now, before going to apply this Laplace transform, what is this importance of Laplace transform? Why you are specifically studying this Laplace transform? If you observe this signal, e power at u of t, already we have a Fourier transform for analyzing non-periodic signals. Now, it is a generally non-periodic signal, but if you see, it is not absolutely integrable. If you want to apply a Fourier transform, it must be absolutely integrable. It is one of the conditions in the Dirichlet condition. So, the Fourier transform fails in this type of signal. It is a unstable signal. If you draw the signal from 0 to infinity, it is going to be incremented continuously. At time t equal to infinity, also this value is going to be get infinity. So that's why this type of signals, the Fourier transform fails. For this type of signals, the Fourier transform fails. So that is the importance of this Laplace transform. So this Laplace transform, we are going to be calculate not for entire range of values of sigma, up to certain range of values of sigma, the Laplace transform is going to be exist. That's why there is a word along with Laplace transform. That word is a region of convergence. That word is region of convergence. So within this region of convergence, only the Laplace transform is going to be exist. So now if we consider a Laplace transform formula, the Laplace transform of x of t is equal to, generally it is from minus infinity to plus infinity, f of t into e power minus st into dt. It is a general Laplace transform formula. Now here the f of t has given e power at u of t. There is a data listed here, e power at u of t. Now what is the u of t? You know unit step function. This unit step function is 1 for time t greater than or equal to 0. And it is 0 otherwise. So the signal is a positive sided signal. The signal is a positive sided signal. It is extended from 0 to infinity, but it is not a stable signal. It is an unstable signal. Now, the limits are changing from minus infinity to plus infinity to 0 to infinity. We need to apply the limits from 0 to infinity, e power at e power minus st into dt. Now, there is, if we take exponential term, minus is a common in that. So, s minus a into t. So, integral 0 to infinity, e power minus of s minus a into t into dt. Now, if you apply integration for that, integration of e power minus s minus a into t is nothing but e power minus s minus a into t divided by, with respect to t, we are integrating. So divided by s minus a minus s minus a. So it is simply e power minus at dt integration. E power minus at dt integration is equal to e power minus at by minus a. That is a simple concept. In place of a, we have a s minus a. We substitute that limits. It is going to be get upper limit e power minus of s minus a into infinity minus e power minus s minus a into 0. Now we need to write, there it is not available, but you, whenever you practice, you need to substitute that one, you need to write this. Now the importance of ROC is here only. Now if you substitute the upper limit, e power minus of s minus a into infinity, there is a minus infinity. Suppose if we take this s minus a is less than 0, condition, because the ROC is a condition here. Suppose this s minus a is less than 0, already there is a negative, this s minus a is also negative, minus into minus plus, we are going to get e power infinity. This is not going to be exist. So for what range of values of sigma it is going to be exist means, the s minus a is definitely greater than or equal to 0, or s minus a is greater than 0, not equal. S minus a is greater than 0. Whenever s minus a is greater than 0, it is a positive. Now s minus a term is positive and e power minus infinity is going to be get 0. And remaining term e power minus 0, anyway 1, minus minus gets cancelled. So finally we are going to get the Laplace transform of e power a to u of t is 1 by s minus a. Again, you, after getting this, we were converted into time domain to s domain. Then suppose there is a numerator polynomials, you need to find out the roots for that, and as well as denominator polynomials, you need to find out the roots. After finding the roots, the numerator roots are going to be called zeros of the particular in Laplace domain, and in the denominator the roots are poles in the particular domain. So the poles and zeros are very important for analyzing this S domain. Now coming for this ROC, just before I said, the s minus a is definitely greater than 0. Then only this Laplace transform exists. So that's why you need to consider this ROC here. You need to consider this ROC here, region of convergence. Now, whenever s minus a is greater than 0, what is the s? It is a sigma plus j omega. Sigma plus j omega is greater than a. So here, in the right hand side, only there is a real part. So we need to compare real part with. So in the left side, there is sigma plus j omega. So j omega, omega is greater than 0. So there is no any issue with that. So this S means sigma, because sigma plus j omega, imaginary part right side not available. So we consider it is in left side, real part of S is greater than A. So real part of S is nothing but sigma. Now the overall ROC is real part of S is greater than A or sigma greater than A. That is our intention. Now, if we want to draw the S plane, it is important. If you want to draw the S plane on x-axis, it is a real part of S. It is nothing but sigma. On y-axis, imaginary part of S, nothing but j omega. Now, there is a, we just said that the denominator roots are called poles. The roots are going to be make it is equal to 0, and after making s minus a is 0, we are going to get a pole at s is equal to a. That s is equal to a, nothing but sigma is equal to a. You don't confuse here. So because omega is 0 at that case, omega is 0. So omega is 0 is on x-axis. You need to locate a sigma is equal to a. We need to locate a pole like a cross mark. A pole is like a cross mark. And then you observe the ROC condition. It is real part of S is greater than A. So greater than A means what? Right sided. So that shaded region, entire from minus infinity to plus infinity of imaginary axis, on x is equal to sigma is equal to A, entire right sided portion is ROC for this particular problem. So if you observe here, three conditions. First one is The signal is an unstable signal. The Fourier transform fails for analyzing this unstable signal, but we are coming for Laplace transform. The Laplace transform is exist up to certain range of values of sigma. Up to certain range of values of sigma. Another important point, it is a right-sided sequence, right-sided signal. So if we see ROC, the ROC is a right-sided. The ROC is also right-sided. You remember one more point, the ROC does not contain any poles. The ROC does not contain any pole because the pole is at S is equal to A. That is nothing but sigma is equal to A. That is nothing but real part of S is equal to A. But the ROC is after A. So it is the main remembering points in Laplace transform. First one is whether it is stable or unstable. And then the ROC, whether it is the signal, whether it is a right-sided signal or left-sided signal. And then ROC, whether it is the right-sided ROC, left-sided ROC. You need to remember these 3 points, then the Laplace transform is very easy. So, today I am going to confine up to this ROC concept, this particular concept, because it is the first problem. Whenever if you understand this ROC concept, then only remaining entire unit is going to be depend on this only. Because Laplace transform is a special for this question only. Because whenever there is a unstable signals or unstable systems, it is going to be analyzed. So one more important point is here, the Fourier transform, whatever the transformation previously we have seen Fourier transform, it is a special case for Laplace transform. Whenever sigma is equal to 0, Fourier transform and Laplace transform both are same. So whenever if you're going to be analyze the signal in Laplace transform and S domain, that is sigma is equal to 0, it's nothing but Fourier transform. And usually in the student point of view in the exams, sometimes they may feel Fourier transform is difficult. So better after completion of subject, you thorough with the Laplace transform. If you are thorough with the Laplace transform, Fourier transform also will get. Because if S is equal to, in the sigma is equal, in the S is equal to j omega, if you substitute, nothing but Fourier transform. Okay? We will see in the next class.